Good evening, everyone, and good afternoon to those signing in from the Americas. We'll now get started with this webcast. So, to give you a quick overview of the proceedings for the evening, uh, we'll start with a quick introduction by the host. That's me, Anant, and this will be followed by the presentation by Henrik Koblauch, who is an assistant professor at the School of Physiotherapy at the University of Copenhagen. So Henrik has been applying musculoskeletal modeling and simulation to study loads in the lumbar spine for airport baggage handlers when they are in the action of loading heavy bags into aircraft. So his talk can roughly be divided into two parts. The first being a more general validation of a lumbar spine model, and the second part being an application of this validated model to study lumbar loads in airport baggage handlers. This will be followed with some concluding remarks from me, and we will then move on to the question and answers. So for those of you who are new to this webinar system, just a few basics. You would see a control panel, which should most likely be on the right side of your screen. And you can expand or collapse this panel by clicking on the red button. If you have any questions as the talk progresses, please do not wait until the end of the talk to ask your question. You can open the questions panel, which should again be visible in your control panel, and just type away, and your question will be answered at the end of the presentation. In case we do not manage to get to your question in the interest of time, we will surely follow up through email. And in case you lose the questions panel, no need to panic. You can just go up to the view button and then recover your questions panel again. For those of you who aren't familiar with the Anybody modeling system, just a quick introduction. It is, of course, a software for performing musculoskeletal analysis and simulations. And it comes along with the Anybody Managed Model Repository, which we often abbreviate as the AMMR. And it is essentially just a library or a collection of models, fairly detailed models of different parts of the human anatomy, which are then put together to form a full body model. And this library is curated by us here at Anybody Technology, and we keep updating it from time to time based on the latest research findings and publication results. The software gives you a wide range of simulation options, some examples of which are the use of motion capture to define your movements, the use of ground reaction and force prediction algorithms for cases where contact forces are either not known or are difficult to measure. You will see an application of this in the content presented in this webinar as well, as Henrik will explain very soon. Using medical imaging to create highly patient-specific models, and running man-machine simulations. So if you have a person on a cycle and you want to simulate the man and his environment as a single system, so that is something that the software specializes in as well. These are the most common applications that we see the software being applied to, although there are probably many more niche applications, which probably are, it's difficult to list all of them over here. You could imagine Henrik's talk is probably a combination of what you see on the extreme right and the extreme left, workplace ergonomic analysis using motion analysis techniques. Just a brief overview of the building blocks of an Anybody simulation. These are the three main components. The first being the body model, which can be the human models in the AMMR, or any other models that you can construct bottom up. A model of the environment, which is optional in case you're simulating a prosthesis or an orthosis, which connects to the human and affects the movement in some way. You can have these models as well within Anybody. And of course, the motion and the forces, which define the kinematics and kinetics of the movement task. So the software gives you certain functionalities which let you combine the environment and body models into a single model, upon which these motion and forces can then be imposed. And then you run an inverse dynamic simulation, which uses optimization techniques to solve the muscle recruitment solve the muscle recruitment problem. And the results are you get time varying information on the internal body loads, such as the muscle forces and the joint forces. So for many users, this would typically serve as as the final outputs that they're seeking. But then you can go ahead and do some post-processing. So, for example, anybody gives you it can export data in some formats which are compatible with some finite element tools such as Abacus. So you can go ahead and analyze the stresses and strains in your bones that are being caused by these internal body loads. Or alternatively, if you are interested in optimizing the design of your environment, such as building an exoskeleton which induces a certain desirable effect on the musculoskeletal system, such as minimizing muscle forces or minimizing joint contact forces, you can run these iterative optimization studies within any body as well and come up with the most optimal design for the motion environment. So with that quick introduction, I will now give the word over to Henrik, who will enlighten us on the lumbar spine loads when loading an aircraft.
Hi, everybody, and thank you very much for attending this webinar. I'll just get going if my computer lets me. Thank you for the introduction, Anat. My name is Henrik Koblauch, and the work I'm going to present today is part of my PhD study, which was done at the University of Copenhagen. And this study was a smaller part of a larger study, which is called the Copenhagen Airport Cohort. And this study aimed to analyze and describe causes of musculoskeletal injuries in airport baggage handlers in Copenhagen Airport. This cohort consisted of roughly 3,400 present and previous baggage handlers and a matched control cohort of some 70,000 matched subjects. So I spent a lot of time at the airport with these guys throwing baggage around. So please pack your stuff carefully if you don't want to lose it. So this is a guy emptying a baggage container inside the baggage hall. So either these guys are inside the baggage hall or outside on the ramp, which this guy is. He's inside the belly, inside the luggage compartment of 737, a Boeing aircraft. And as you see, he's lying on his knees, which is a preferred position when they're inside the luggage compartments. This guy is outside the aircraft, emptying a baggage cart onto the conveyor, which subsequently takes the baggage to the hull. All right, so the background for this study was that we know from the literature that there's a high prevalence of musculoskeletal complaints in baggage handlers overall, and especially in airport baggage handlers. And the job as a baggage handler is mainly characterized by a lot of heavy lifting and a lot of heavy lifting in non-neutral working positions, which then leads to obviously asymmetrical lifting because they're twisting and turning inside the baggage compartment, as you saw. And the average suitcase that the baggage handler lifts weighs around 15 kilograms, which then averages up to around 4 or 5 tons of baggage lifted every day, sometimes even up to 10 tons. Furthermore, we know that heavy lifting and lifting in awkward position increase the load on the lumbar spine specifically, and furthermore, the increased compression force is what's increasing dramatically, and we know that this increased spinal load is a risk factor for developing non-specific low back pain. So the purposes of my study was, first of all, to develop a generically useful tool to examine the specific lumbar compression validly. And furthermore, we wanted to apply this model to common work tasks, to everyday life for the baggage handlers. So we wanted to investigate the spinal loading in common work tasks for airport baggage handlers. So what we did was that we wanted to compare the model results with something that we believed in. And what do we believe in? We believe in vivo studies, basically. Wilke and co-workers previously published a couple of papers on the intradiscal pressures during various daily activities. And what they did was that they inserted this pressure gauge into the L4, L5 disc of a poor subject, and had him do all sorts of stuff. And as you see here on the X-ray, it's lying nicely in here in the nucleus pulposus. And as you see, they didn't let him rest a lot. They had him do all sorts of different stuff. These are some of the positions that he was put in: maximum flexion, carrying crates of beer in different ways, with the flex back, and sitting upright and sitting slouched. So many different positions were adopted by the subject. And what we did was that we used the Anybody modeling system to build inverse dynamics-based models. And they were all modifications of the standing model, which is freely available in the Anybody managed model repository. All of these models included the highly detailed spinal model, which has been presented by Mark Desai and co-workers, which consists of 7 segments: a thoracic segment, a pelvic segment, and 5 lumbar spine segments. A whole lot of muscle fascicles, and furthermore, which is very interesting actually, a model of the intra-abdominal pressure that can actually relieve some of the compression force on the lumbar spine by creating a passive extensor moment. And our primary outcome was the compression force, and we measured that on the cranial end plate of the L5, as you see here illustrated. We moved a bit around on the reference frames from what was the default setting. The default setting had the origin of the reference frame around the back edge of the forearm vertebralis. And what we did was that we moved it so that the reference frame was now with an origin more or less in the middle of the cranial end plate. And at least the cranial end plate created a plane on which the compression force was perpendicular. Also, we turned it a bit counterclockwise. We rotated it counterclockwise around the Z axis just a wee bit. Also, we were interested in the sensitivity to muscle recruitment criteria. So we used 2 different criteria. We used both the third order polynomial criteria and the min-max criterion. The third order polynomial criterion seeks to minimize the sum of muscle forces cubed, whereas the min-max criterion seeks to activate all involved muscles with as little as possible activity. We then positioned the model in all these various positions that the subject was in the in vivo study. So we had him max flexed, both the subject and the model, and we had the model lift, in this case an aquarium with fish in it, with both close to the body and with stretched arms, flexed and sitting upright, sitting slouched, and standing both upright and bent forward, and also lying supine. Where there was pictures available, we positioned the model as good as possible based on the pictures, but not all of the positions from the Wilke et al. Paper was depicted, so some of the positions were only described in writing, and based on that we positioned the remaining 3 positions. So another problem that came up was that we're measuring or estimating compression force, whereas from the in vivo study we had the intradiscal pressures, and there's no one-to-one relationship between the two. This is primarily due to the heterogenic composition of the spinal disc. So we needed something to make the conversion correct. So what we did was that we took the pressure multiplied by the area of the disc and had this correction constant added to it. In this case it was 0.77, which was suggested by Dreischaft and co-workers, which did a sensitivity study on this and found this correction constant appropriate. However, this was model specific to their model, so it might not apply to our model. So for the results, what you see here are the different positions that we positioned the model in. On the y-axis, the compression force. In the red, or the wear cross, are the in vivo estimates. In the green, the third order polynomial muscle recruitment criterion, and in the blue, the results from the model when the mean max muscle recruitment criterion was applied. And what you see is that when the forces are quite low, the compression forces are quite low, the model tends to underestimate the forces regardless of muscle recruitment criterion. The model comes up with less force than what was actually in the in vivo study. However, when the compression force increases, we see a nice agreement with the trend. So when the in vivo data goes up, when the in vivo compression goes up, the modeled compression increases as well. And furthermore, what we see is that it seems like that the mean max criterion performs slightly better than the third order polynomial criterion does. This is also depicted on this slide. It's a bit busy. I apologize for that. But what is really interesting is what I'm highlighting here, that when the forces pass 1500 Newton, the mean max criterion estimates quite accurately the forces from the in vivo measurements. So with forces passing 1500 Newtons, the mean max criterion estimates forces within 13% and even less than 13% of the in vivo data. Here the third order polynomial is a bit more off. Good. So what we found here was that there was a high degree of agreement between the in vivo intradiscal pressures and the model compression force, especially when applying the mean max muscle recruitment criterion. Also, there was a good trend agreement regardless of the muscle recruitment criterions. I took the liberty of doing a correlation coefficient. I know it's not a very strong measure, however, they are sky high, 0.995 and 0.993 for the two muscle recruitment criteria. And it seems like as the forces increase, the agreement even improves. So to the limitations and the strengths. This is where the magic happens. So these intradiscal pressures were measured during some sort of dynamic movements, whereas our model calculated the load in one time point only. Given that the subject of the in vivo study had this pressure gauge inserted into a spinal disc, he may not have moved very fast, but still it was during in a dynamic setting, whereas the model was only calculated in one time point, as I said. Also, the positions of the model were not exactly similar to those in the in vivo study. This was due to the lack simply of kinematic data from Wilke and co-workers. This is actually a pity, because if joint angles or segment angles were provided, we could have positioned the model exactly in the correct position. Furthermore, segment properties of this model was based on the anthropometric fractions suggested by Winter, rather than actual data from the subject. This might influence the results as well. However, this is still comparison with in vivo measurements, and as I said to begin with, what do we believe in? We believe in stuff that's measured in real life. So this is actually quite strong that the agreement is so high. So to conclude this first part, the model showed quite high agreement with the intradiscal pressures retrieved in vivo by Wilke and co-workers. Also, the model responded adequately to the changes in positions. So when the in vivo pressures increased, so did the estimates from the model. However, some of the assumptions from the model can question the validity of this study. So, still, we were quite encouraged by the high agreement of the model with the in vivo data. So we carried on to investigate the spinal loading in a real-life setting during work tasks for baggage handlers. And what we did was we invited a professional baggage handler into the lab. He was male. There are only males employed at Copenhagen Airport as baggage handlers at the moment. He was 48 years of age, 1.81 m and 87 kilograms. This was an average of all the baggage handlers that answered a questionnaire, which was just below 3,000 questionnaires, where they self-reported their body height and body mass. We asked the baggage handler to perform a large variety of different lifting techniques and positions. However, in this study, I'm going to go into the stooped position and the kneeling position of throwing suitcases around. We had the subject lift 20 kilogram, 15 kilogram, and 10 kilogram suitcases. We recorded the kinematics with a standard, however custom-built motion capture system consisting of 8 synchronized high-speed, high-definition cameras, which sampled at 75 Hertz, 2 AMT platforms, force platforms when he was standing, and 4 AMT platforms when he was kneeling, 1 under each knee and 1 under each foot. And as you see, we dressed him up as a Christmas tree, equipped him with a full body marker setup of 38 markers on the body of the baggage handler and 3 markers to define the suitcase segment. And to the modeling. We built these inverse dynamics-based models from the Anybody Modeling System version 5.3. These were all based on the gait full body model from the Anybody Managed Model repository. I think it's actually called the mocap model now. We use the kinematic data from the motion capture to drive the model, to move the model around. And in this model, the spinal model was included. As you see here. I'm hearing something, guys. Can you tell me if something's going on?
I hear this as well, and I'm not sure of what it is. Well, it's gone off for now, so let's just carry on and hope it doesn't return again.
Okay, cool. Thanks. I'm sorry for that glitch. I'll just carry on. If I remember where I got to. Oh yeah, the spinal model was included in all of these models and is also included in this gait full body model, which is available at the model repository. In both the kneeling and the stoop task, the grip on the suitcase was modeled in accordance with the actual grip that the baggage handler had on the suitcase he was about to move. So in both cases, the right hand was linked to the suitcase with a revolute joint because he had the right hand gripping a handle on the suitcase. The left hand, however, was kind of squeezing the suitcase in the experimental trials. So we modeled that accordingly using this conditional contact, which Michael Skipper-Anderson has presented on, which can predict forces in various situations. This is what you see here. We had on the hand 3 points, which when they entered this large gray cylinder were able to produce force in the normal directions of the points. This means in this case that the baggage handler was able to squeeze the suitcase, which would then balance the remaining degree of freedom from the revolute joint. So our data output were following. We mainly concentrated on the compression forces, which was measured in the negative Y direction. Also, we recorded the shear, anterior-posterior shear forces, which was the positive X direction, and the rotator moment, which was the counterclockwise Y moment. Also, in this model, in these models, the reference frame was modeled accordingly to the validation study that I just presented. So the forces were estimated on the cranial end plate of the L5. So these guys have been my best friends over the last couple of years. I've spent a whole lot of time in their company. This is obviously a model of a baggage handler in kneeling position handling the luggage. And what you see on the suitcase is the same cylinder as I had magnified just before, where the baggage handler is able to produce force so he can squeeze the suitcase. Also, the gray cylinder on the floor to the left, and however it's white on the right side, is mimicking the floor. So whenever the suitcase is standing on the floor, it carries itself on this conditional contact. So it's only when he lifts it off the floor that he has to carry the suitcase, per se. And here is the stooped model. Again, you can see reaction forces from the floor, and I moved the cylinder from the end of the box, but again, you can see the reactions from the hand. And the results, again, a busy slide, I apologize. However, I'll try to talk you through it. What is mainly interesting here is that the 10 kilogram suitcase in the stoop position produced the highest compression force overall, up to 16,600 newtons of compression between the L4 and L5. Also, the other two stooped positions produced quite high compression forces. Also, the kneeling task produced quite high compression forces, as you see. However, not as high as the stoop task. It's also in the stoop task that the largest shear forces occur, 578 Newton of shear anterior-posterior shear force. So as I said, the highest compression occurred in the stoop task where the baggage handler lifted a 20 kilogram suitcase. That is actually quite counterintuitive, and it didn't really make sense to us until we thought that it might be that he knew how heavy the suitcase was when he was about to lift it. I didn't randomize the order of the suitcase he was lifting, so he was always lifting the heaviest, the 15 kilogram, and then the 10 kilogram suitcase at the end. So this might be a reason that he knew the suitcase was actually lighter than the two he had already lifted. So he might have accelerated the suitcases more and thrown the suitcases harder, which then subsequently would have produced more force, more muscle force, and then more compression force in the lumbar spine. I could have randomized, of course, the order of the suitcases. However, he was only lifting 3 different suitcase weights, so regardless of randomization, he would always know how heavy the last suitcase was, and this could induce some bias at least. In all cases, in all tasks, the compression force that we found in this study exceeded the recommendation by far, the NIAS recommendations, which are 3,400 newtons. They were exceeded by far. Also, the Dortmund recommendations, which takes both age of the subject and the sex of the subject into account, they have a maximum allowable compression force at 6,000 Newton for a 20-year-old man, and that is also exceeded by far. And it even exceeds the average maximum compression tolerance from cadaver studies from the literature. Jaeger and co-workers did a literature review of all these cadaver compression force studies, and found an average of 6,180 Newton compression force. However, the range of these compression forces was quite wide, so some of the weaker segments collapsed under only 800 newtons, and some of the stronger segments could withstand up to like 12,000 newtons. But still, the forces recorded in this study would exceed even the strongest of the cadaver segments. However, we found small shear forces. As I mentioned, the largest shear, anterior-posterior shear force, was some 580 newtons. And according to Gallagher and Maras, 1,000 Newton is allowable for single cycles, which is less than 100 a day, and up to 700 Newton is allowable for continuous work, which characterizes the baggage handler work. So, strengths and limitations of this last study. This is a one subject, one trial study, so the technique of the baggage handler may vary. It may vary between baggage handlers and even between tasks. However, we look at this as more of a proof of principle. This model allows for the analysis of three-dimensional asymmetrical lifting, and it is generically useful to investigate any kind of lifting tasks. So it should be able to be, it should be applicable to any kind of lifting task, regardless of profession or regardless of anything, basically, as long as the object that is lifted can be modeled to fit with the model, it should be possible to investigate the lifting. And what is also a strength of this model is that it's very high level of detail. It has multiple wrapping muscles that wraps regardless of the way the lumbar spine twists and turns, so that the moment arms of the muscles are quite reliable. Furthermore, it's a multi-segment moment equilibrium model, so the moment of the lumbar spine is divided onto the 5 lumbar segments. Some perspectives. As I just mentioned, the model can be used to analyze any kind of lifting situation. And what I want to do next actually is that I want to optimize some of these lifting tasks to see if anything can be tweaked a bit to optimize or to reduce at least the spinal compression, or to reduce the muscle force used. This could be very interesting. Also, for the employers, that the data from this study could be used to prioritize job rotations. Say that one task produces more spinal compression than another task, then they may emphasize that the baggage handler should be kneeling instead of stooping in the baggage compartment when they are in the baggage compartments. And furthermore, the data from my study can be used in the larger registry-based epidemiological study that the Copenhagen Airport cohort study is. And coming towards the end here, I'll be happy, obviously, to answer any questions that might come up that you don't get a chance to ask during the Q&A session. So just write me on my email address displayed on the screen here. And lastly, I want to thank my academic supervisor, Erik Simonsen, Mark Dessé, and Michael Skipper-Andersen for huge help with the models. Also, the Danish Work Environment Research Fund that funded the work, and especially Anybody Technology for giving me the opportunity to present my work. Thank you very much.
Great, Henrik. Thank you for that very interesting presentation. And I will now begin the battle with my system to try and make myself the presenter again. All right, so this would be a good time for anyone who has questions right now. This is a great time to ask them. And just to give you some time to, while you think about those questions that you would like to ask, just a few concluding remarks. With regards to our schedule for the webcasts, we don't have any plan for the month of December. However, we will be back with some interesting topics around the end of January or probably the beginning of February. To learn more about previous webcasts, and they're all uploaded there in their full-length versions. You can check out our YouTube channel. You can just search for the channel called Anybody Technology, and you'll find all of them listed there. You could visit our website, anybodytech.com, for more news on events, dates, and a list of publications that have been made, which would give you an idea of the different applications that you can have with these models. If you're interested in any script, which is essentially the programming language on which the Anybody modeling system is based, you can visit the anyscript.org website. which houses both a wiki page as well as a forum where you can get a feel for what the technicalities of behind using the Anybody modeling system. So moving on to questions, let me just get Henrik back here again. Just give me a second. Hi, Henrik. Can you hear me?
Hi. Yeah, I'm back.
Great. So we get started with the questions now. And so the first question is, like, we actually have a few questions along a fairly similar theme, which is trying to understand the contact model between the hand and the object. And I'll probably just take this myself because I think you gave a very nice description of that during the talk. And for people who are interested in learning more, which seems to be the case from most of these questions, please, there was a webcast by Michael Skipper Anderson from the University of Aalborg. And this webcast you can find on our YouTube channel that I just mentioned in the last slide. And there is also a publication by René Fluid, which is referred to in the webcast in case you want the full reference. Or you can even find the publication on our website. So with that question done, let's move on to some more. So someone
Can I just comment on these conditional forces?
Please.
Actually, this is mentioned in Michael Skipper Anderson's webinar as well. They're quite neat actually because they will allow motion capture, transfer of motion capture data into this Anybody model. Even without the use of force platforms. So if we can predict the ground reaction forces without the force platforms, it opens up a whole variety of new possibilities of doing field data collections here.
Thank you, Henrik, for elaborating on that. So is the biomechanical models that you used, are they at what level do they incorporate the dynamics of the task? So in what senses could your model be considered dynamic?
Well, it depends on which models we are addressing here. Okay. The models from the validation study are more or less static. Okay. However, because the compression force and the remaining forces are calculated in one time point only. However, the models from when the baggage handler chucks the luggage around are dynamic. You saw them move.
Yep.
So they move and they respond to different kinds of movements.
Got it. A very interesting question over here is, did you have the chance to study the pressure in other vertebrae? So which pair of vertebrae would probably exhibit the greatest pressure in the spinal column?
Yeah, that's a good question. The data is readily available in the Anybody modeling system, so it's quite easy to extract. I obviously peeked a bit to the other vertebrae, and it kind of looks like that the gravity has quite an impact on this. So in general, and this is generally speaking, the forces are a bit higher in the L5-S1 joint as to the L4-L5 joint.
All right, thank you. Moving on to the next question. How sensitive are the relative compressions and anterior-posterior shear forces to the assumed sagittal orientation of the L4-L5 motion segment? I could repeat that if you'd like.
No. I think I'm good.
All right.
The question is on how the lumbar vertebrae move with regard to the pelvis, right?
I think it's about how sensitive are your computed compression and shear forces to the assumed motion of the L4-L5 motion segment within the spine model.
Okay. So let me start a bit somewhere else.
Sure.
We moved, as I said, a bit around on the reference frame,
Yep.
and actually, quite by chance, this reference frame ended up more or less with the origin
Yep.
on top of the spherical joint that is keeping the vertebrae together.
Yep.
So it's not too sensitive to this relative movement.
Okay. But was there I'm assuming that because there wasn't using motion capture, you cannot really track the exact movement of each vertebral segment. So was there
No,
a
no.
method that you used to approximate like the relative motion of each segment with respect to each other?
Yes, yes. It's incorporated somewhere deep in the any script in the model, but it resembles bending a beam basically. And
Okay.
if you look at the lumbar spine bending, it
Yep.
bends the most at the L1, L2, and it bends less and less actually coming quarterly.
Okay. So do you think changing the relationship between the different segments, do you think that would, or rather, how would you expect that to impact the computed forces?
Um, if there was more movement in the lower segments, I would expect a larger movement and therefore more muscle force and therefore more compression,
Okay, great,
basically.
great. Thank you. So moving on to our last few questions. Uh, can you tell how great the influence of those approaches? So the approach that you used for predicting your reaction forces, how would that impact I think by reaction forces, I think he means the hand luggage contact
Mm,
forces that were predicted using the algorithm. So how
mm.
do you think this would affect the outcome of the study?
Yeah. Just let me start by stressing that we used measured ground reaction forces from our force plates, and we calculated the forces on the lumbar spine bottom up. So
Mhm.
I wouldn't expect that would change anything because we calculated from the hands to the shoulder and to the thorax, and the rest was calculated bottom up.
Got it, got it. So you're right. I understand. Yep. Uh, so someone else thinks that this is very interesting work, and and they want to know whether you have considered what would be the difference. So would you expect the trends in the lumbar forces to be any different between right-handed and left-handed individuals? And if yes, what would your gut feeling predict in that case?
That's a very interesting question. Thank you very much for that. As I just mentioned, we calculated bottom up, so my guess it is that it wouldn't change too much. But what could change something was that if the environment constrained that the the suitcase had to be lifted in some direction and you were left-handed, that could favorize maybe left-handers, but that's speculative. Yeah, my best answer would be not much.
All right, great.
Yeah.
So as for the last question, this is something that I wanted to ask you. Uh, how do you think, so do you think that the results that you get from these simulations, do you think that they could one day affect the sort of training policies and sort of workplace policies for baggage handlers? So for example, if a certain technique of loading bags onto the aircraft, if it seems to be producing excessive stress, which is harmful, would you see these simulations as, as possibly being a way of guiding us towards what the best technique is and probably training these baggage handlers to use those techniques? What are your comments and thoughts on the progress of this research in the future?
Yeah, that's very interesting. I actually had a project sketched where I wanted to do some of the stuff you're asking about. Especially the optimization of the lifting task is very interesting to me. So if we can come up with a technique that is optimal, or that at least reduces the stress on the lumbar spine, that would be very interesting. The difficult part, I think, is to get that out in real life. I think it's very hard to teach people what to do, because in some way they are definitely optimizing themselves, even though they're not using computers and stuff. They're optimizing their motor control. But it would be very interesting, very interesting.
Great. Again, Henrik, thank you very much, and I'm sure I speak on behalf of everyone, thanking you for this wonderful presentation, and also for patiently taking up all these questions and answering them very diligently. For those whose questions weren't answered, we'll surely try to get back to you with the answers by email. And on that note, thank you all for listening in, and Merry Christmas, Happy Holidays, and we'll probably catch you very soon next year with some interesting webcasts. Thank you.